Cold in space doesn't work like cold on Earth. There's no wind, no ice, no way for heat to drain out of you the way it does on a winter night. And yet space will still kill you, just not the way you think. So how does absolute emptiness become the most lethal thing in existence? If you love having your mind genuinely expanded by real science, make sure to give this video a like. Now let's get started. Cold isn't what you think it is. It isn't a substance, it isn't a force, it's an absence, the void left behind when heat runs away. There are no cold particles flowing into you when you hold ice. There is only heat flowing out. Cold is just the word we use for that loss. It's just a perception, and in space, that distinction becomes everything, because in space, heat can only escape one way. Not through air, there is none. Not through contact, since there's nothing to touch, only through radiation. Slow, invisible, electromagnetic radiation bleeding outward into the dark, which means your body, floating in the void, wouldn't freeze the way you imagine. It would hold its warmth, stubbornly, for minutes, maybe longer, radiating heat away in silence, degree by degree, until eventually, patiently, inevitably, the cold won, and the temperature it would be losing heat to. 2.7 Kelvin, that number is not arbitrary. It is the temperature of the oldest light in the universe, the cosmic microwave background. Ancient photons from 380,000 years after the Big Bang, stretched by 13.8 billion years of cosmic expansion until they became microwave radiation, invisible everywhere, inescapable. The universe isn't cold because it's empty, it's cold because it's old, still faintly glowing from its own violent birth. Just barely. It was found by accident. 2 engineers, a radio antenna, and pigeons. Arno Penzias and Robert Wilson at Bell Labs in 1965 couldn't get rid of a faint directional hiss in their equipment. They cleaned it. They removed the pigeons nesting in the dish. The noise remained. Because it wasn't noise, it was the echo of the Big Bang. They won the Nobel Prize now. 2.7 Kelvin is the floor, the baseline of the universe. But what if I told you something natural, something out there right now, has gone below that floor? That there are places in the universe colder than the background temperature of space itself. One of them has a name almost too perfect for what it is. Its name is the Boomerang Nebula. We're going to get to the Boomerang Nebula in just a moment. And trust me, when you hear what makes it so cold, your jaw is going to drop. And have you ever thought about what would actually happen to a spacecraft if it ventured into deep space? Not just the cold, but everything. The radiation, the vacuum, the time. I actually made a video exploring exactly that. It's on the card above. We explore how long a starship would actually survive in deep space, and it pairs perfectly with what we're talking about today. The link is in the description and pinned on the comments. Now let's finally talk about the Boomerang Nebula. Even the name sounds like something out of a science fiction novel. But this object is completely real, and it holds a record that, when you truly understand it, feels almost impossible. It is the coldest known natural place in the entire observable universe, not the coldest place we've created in a laboratory. Not the coldest place in our solar system, the coldest known natural place anywhere, in a cosmos that stretches over 93 billion light-years across in the observable portion alone. And it is colder than deep space itself. Let that sink in for just a moment. We just established that deep space sits at 2.7 Kelvin, barely above absolute zero, bathed in the ancient afterglow of the Big Bang. The Boomerang Nebula somehow sits below that. Its temperature has been measured at approximately 1 Kelvin, 1 degree above absolute zero, colder than the cosmic background radiation that fills every corner of existence. How is that even possible? To understand it, you need to know what a nebula actually is. The word comes from Latin, meaning cloud or mist, and that's essentially what a nebula is, a massive cloud of gas and dust floating in space. Some nebulae are the birthplaces of new stars. regions where gravity slowly pulls matter together until it ignites. Others are the remnants of stars that have died, the scattered, glowing wreckage of a life that burned for millions or billions of years. The Boomerang Nebula falls into a specific category called a protoplanetary nebula. It's what happens in the late stages of a star's life, not quite a full planetary nebula yet, but well on its way. The central star, which is in the process of dying, has been violently ejecting its outer layers into space, and not slowly. The gas streaming outward from the Boomerang Nebula is moving at roughly 170 kilometers per second. That is extraordinarily fast for a stellar outflow, around 612,000 kilometers per hour. Now here's the physics that creates the cold. When gas expands rapidly, truly rapidly, it cools. This is the same principle behind how your refrigerator works, how air conditioning works, how aerosol spray cans feel cold when you press them. When gas is forced to expand into a larger volume quickly, the molecules spread out, collide less frequently, and lose kinetic energy. Temperature drops. This is called adiabatic cooling, and in the Boomerang Nebula, it's happening on a scale almost too enormous to picture. The gas being expelled from the dying central star is expanding so rapidly over such a vast distance that it has cooled below the temperature of the cosmic background itself. The universe is trying to warm it. That 2.7 Kelvin glow of the CMB is washing over it constantly, but the expansion is happening faster than the CMB can reheat the gas. So this expanding cloud actually absorbs the CMB rather than emitting radiation like most objects do. That's how something natural gets colder than space itself. Not by some exotic physics we don't understand, by simple, elegant thermodynamics operating at a truly cosmic scale. The Boomerang Nebula was first observed back in 1980 by astronomers Keith Taylor and Mike Scarrett using a telescope at the Anglo-Australian Observatory. They named it the Boomerang because, through their ground-based telescope, it appeared to have an asymmetric, curved shape like an Australian boomerang. Years later, when the Hubble Space Telescope turned its extraordinary eye toward it, the nebula looked different, more like a bow tie or an hourglass shape, leading to some debate about the name. But Boomerang Nebula stuck, and Hubble didn't just give us a prettier picture. It helped astronomers understand the structure more clearly, showing that the outflow wasn't perfectly symmetrical, that something about the central star's environment was shaping the gas in ways that are still being studied today. It sits about 5,000 light-years away from us, in the direction of the constellation Centaurus. 5,000 light-years. The light you would see if you looked at it tonight left that nebula around 3,000 years before you were born. Around the time ancient civilizations were building the earliest versions of the structures we still marvel at today, and yet right now, that gas is still expanding, still cooling, still holding its record as the coldest natural place we've ever found. But here's where the story gets even more layered, because the Boomerang Nebula raises a question that physicists take very seriously. Is there a lower limit to how cold something can get? The answer is yes, and it's called absolute zero. Zero is 0 Kelvin, negative 273.15 degrees Celsius. It is the theoretical temperature at which all thermal motion of particles completely stops. At absolute zero, atoms would have no kinetic energy at all, no vibration, no movement, just stillness. Complete and total thermodynamic stillness. And here's something profound. We have never reached it. Not in nature, not in any laboratory on Earth or anywhere else. Absolute zero is a limit, a boundary that physics approaches but according to the laws of thermodynamics can never actually reach. The third law of thermodynamics explicitly states that you cannot reach absolute zero in a finite number of steps. You can get close, extraordinarily close, but never there. Think of it like a mathematical asymptote. a line that a curve approaches forever but never touches. The coldest temperatures ever produced by human beings have been achieved in laboratories using techniques like laser cooling and magnetic evaporative cooling. In 2003, a team at MIT managed to cool a sodium gas cloud to just half a billionth of a degree above absolute zero. Half a billionth, that is 500 picokelvin, a number so close to zero that it essentially has no meaning in everyday life, and yet, still not zero. There's something almost philosophical about that. The universe sets a hard floor, and everything, every particle, every atom, every cloud of gas, every engineered system floats above it. Some things higher, some things almost impossibly low, but nothing ever touches the bottom. Now, let's zoom back out. Because we've been talking about the coldest places, but the universe isn't uniformly cold, not even close. And understanding the temperature landscape of the cosmos, the dramatic contrast between the cold and the incredibly hot, is what really helps you feel the full scale of what's out there. Consider our own solar system for a moment. If you're standing on the surface of Mercury, the closest planet to the Sun, you might expect it to be uniformly hot, and the day side is brutal. Temperatures can reach up to 430 degrees Celsius during the day, hot enough to melt lead, hot enough to make most metals flow like water. But Mercury has almost no atmosphere to speak of, no blanket of gas to trap heat and distribute it around the planet, so the night side of Mercury drops to approximately negative 180 degrees Celsius. That swing from 430 above to 180 below happens on the same rocky world, separated only by the line between sunlight and shadow. That's already staggering. But it's nothing compared to what happens further out. Move beyond the orbit of Neptune, the outermost recognized planet in our solar system, sitting roughly 4.5 billion kilometers from the Sun, and you enter what's called the Kuiper Belt, a vast donut-shaped region of space filled with icy bodies, dwarf planets like Pluto, comets, and ancient frozen debris left over from the formation of the solar system around 4.6 billion years ago. Out there, sunlight is weak, vanishingly faint. The Sun, which blazes so brilliantly in our sky, appears from Pluto as little more than an exceptionally bright star. Surface temperatures on Pluto hover around negative 230 degrees Celsius. Cold enough that nitrogen, which makes up the majority of Earth's atmosphere and is a gas at room temperature, freezes solid on Pluto's surface and forms glaciers, nitrogen glaciers. Let that image sit with you. A world so cold that the very air of our planet would freeze into ice underfoot, and Pluto is still inside our solar system. Go further, past the Kuiper Belt, into the Oort cloud, the distant, spherical shell of icy objects that surrounds our solar system at distances ranging from perhaps 2,000 to 100,000 astronomical units from the Sun. 1 astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers. The outer edge of the Oort cloud may extend 1/4 to 1/2 of the way to the nearest star. Out there, the Sun is essentially irrelevant as a heat source. You are, for all practical purposes, already in interstellar space. And temperatures out there begin to approach the background temperature of the cosmos, that ever-present 2.7 Kelvin baseline. But here's what's fascinating. Even in those outer reaches, you're not alone in the dark, because the universe, for all its cold and emptiness, is filled with something ancient and ubiquitous and deeply strange, radiation, not just the CMB, but other forms too, cosmic rays, high-energy particles, mostly protons, traveling at close to the speed of light, streaming through the galaxy from supernova explosions and other violent events, X-rays from distant black holes, gamma rays from colliding neutron stars. The universe hums with energy at every wavelength, and even in the most remote and lonely regions of space, that energy is present. It's one of the great paradoxes of the cosmos. Space is cold beyond anything we can truly experience, and yet it is absolutely saturated with radiation. It is simultaneously the most barren and the most energetically active environment imaginable. We are surrounded right now by this. Right here on Earth, in whatever room you're sitting in, cosmic rays are passing through your body at this very moment. Dozens every second. Relics of stellar explosions from thousands of light years away, arriving here after journeys measured in millions of years. You are being touched by the universe constantly, whether you feel it or not. And isn't that extraordinary? We think of space as something out there, something beyond us, something we have to build rockets and spacecraft to visit. But the cosmos doesn't wait for an invitation. It reaches into our world constantly, in the form of light and particles and radiation that have crossed unimaginable distances just to pass through the room where you're sitting right now. You are already in contact with the universe. You always have been. That sense of connection, of being not separate from the cosmos but genuinely part of it, is something we're going to keep returning to throughout this video. Because the story of cold in space isn't just a physics lesson, it's a reminder of where we are, of how remarkable it is that on this one small, warm, rocky world, orbiting an ordinary star, in an unremarkable corner of a galaxy containing hundreds of billions of stars, creatures like us evolved. Creatures capable of measuring the temperature of a nebula 5,000 light-years away. Creatures who looked up at the faint hiss of ancient radiation and recognized it as the whisper of creation. That's not a small thing, that's everything. Now, we've talked about how cold it gets in the natural universe, but there's another layer to this conversation that most science videos skip entirely. Because the cold of deep space isn't static. It isn't the same everywhere, and it certainly hasn't always been this cold. The universe has been cooling since the moment it was born, and it will keep cooling for a very, very long time. Where it ends up, trillions upon trillions of years from now, is one of the most haunting and beautiful ideas in all of cosmology. Let's talk about time, not the kind of time we deal with in everyday life. Not years or decades or even centuries. We're talking about cosmic time, time measured in billions and trillions of years, time so vast that the entire history of human civilization, every empire, every invention, every war and discovery and work of art fits into a single, barely visible sliver at the very beginning, because to truly understand the cold of space, you need to understand where that cold came from, and where it's going, and what the universe will look like when it finally, after an almost incomprehensible stretch of time, reaches its coldest possible state. This is the story of the universe's temperature, from its first breath to its last, and it begins with heat, unimaginable, world-ending, physics-breaking heat. In the very first fraction of a second after the Big Bang, we're talking about a period so brief that it makes a microsecond look like an eternity. The universe was incomprehensibly hot. Physicists estimate that in the first instant, temperatures may have reached something in the neighborhood of 142 nonillion Kelvin. That is 1 followed by 32 zeros. A number that doesn't just exceed our everyday experience, it exceeds the limits of our current physics. We call this the Planck temperature. It's the highest temperature that our existing theories can describe. Beyond it, our understanding breaks down completely. General relativity and quantum mechanics, the two greatest frameworks humanity has ever developed to describe reality, stop working together at that point. They give contradictory answers. They don't speak the same language anymore. So when people say we don't fully understand the Big Bang, this is part of what they mean. Not just that it was complicated or that we lack data. It's that the very tools we use to understand the universe reach their limits right there at the very beginning. What we do know is that almost immediately, within the first tiny fractions of a second, The universe began to expand, and as it expanded, it cooled. Rapidly at first, then more gradually, following a curve that cosmologists can actually trace and model with remarkable precision. In the first second, the temperature dropped from those unimaginable heights to around 10 billion Kelvin, still hot enough that matter and antimatter were being created and destroyed constantly, photons spontaneously converting into particle-antiparticle pairs and then annihilating each other again in a constant, furious cycle. The universe was a roiling sea of energy and elementary particles, too hot and too dense for anything stable to exist. By the end of the first 3 minutes, the temperature had fallen to around 1 billion Kelvin, and something remarkable happened. Protons and neutrons began combining to form the nuclei of the lightest elements, hydrogen, helium, and trace amounts of lithium. This process, called Big Bang nucleosynthesis, happened in a window of just a few minutes, and it set the stage for everything that followed. The universe locked in a ratio of roughly 3 parts hydrogen to 1 part helium by mass, and those proportions are still with us today. When astronomers measure the elemental composition of the oldest, most pristine gas clouds in the universe, they find exactly this ratio. It's one of the most powerful confirmations of the Big Bang model we have. Then the universe kept cooling. For hundreds of thousands of years, it remained a hot plasma, a fog of charged particles and radiation so dense that light couldn't travel freely through it. Photons bounced constantly off electrons, unable to move more than a tiny distance before being scattered again. The universe was opaque, filled with a brilliant, blinding glow that no one could have seen through, even if anyone existed to look. Then, around 380,000 years after the Big Bang, something changed. The temperature had dropped to around 3,000 Kelvin, cool enough, barely, for electrons to slow down and be captured by atomic nuclei. Hydrogen atoms formed, helium atoms formed, and with the electrons no longer flying free, there was nothing left to scatter the photons. The universe became transparent almost overnight. In cosmic terms, light flooded outward in every direction. That moment is called recombination, and the light released at that moment, the light that filled the entire universe when it first became clear, is the cosmic microwave background we talked about in Part 1. That ancient light, stretched by 13.8 billion years of cosmic expansion, cooled from 3,000 Kelvin all the way down to 2.7 Kelvin, and it still surrounds us today. The CMB is essentially a photograph of the universe at 380,000 years old, a snapshot of the cosmos in its early childhood, before any stars had formed, before any galaxies existed, before any planets coalesced from swirling disks of debris, just a nearly uniform sea of cooling hydrogen and helium gas with tiny, tiny ripples of slightly higher and lower density, ripples that gravity would eventually amplify into everything we see today. Every galaxy, every star, every world, every ocean and mountain and living thing, it all grew from those ripples. After recombination, the universe entered a period that cosmologists call the Cosmic Dark Ages, and the name is apt. There were no stars yet, no galaxies, no sources of light anywhere in the universe, just vast clouds of hydrogen and helium gas, slowly cooling, slowly collapsing under gravity, gradually condensing toward the density required to ignite nuclear fusion for the first time. The universe was dark and growing darker, cold and growing colder, and it stayed that way for perhaps 100 to 200 million years. Then the first stars were born, these earliest stars, which astronomers call population 3 stars, though none have yet been directly observed, were almost certainly very different from the stars we see today. They formed from pristine gas containing almost no elements heavier than helium, because the heavier elements hadn't been forged yet. And without those heavier elements to help radiate heat away during the collapse, The gas clouds that formed these first stars couldn't cool as efficiently. This likely meant they grew enormous. Some may have been hundreds of times more massive than our Sun, blazing, brilliant, extravagantly hot, burning through their fuel at a ferocious rate, and then they died. Violently, stars that massive don't fade gently into white dwarfs. They explode as supernovae of extraordinary power, and the most massive ones may collapse directly into black holes. In those explosions, the elements forged in the star's cores, carbon, oxygen, nitrogen, iron, silicon, and dozens of others, were scattered into the surrounding space, enriching the gas clouds that would go on to form the next generation of stars. And so the universe became gradually more complex. Generation after generation of stars lived and died, each one seeding the cosmos with heavier and heavier elements. The universe was building a library of chemistry, one stellar explosion at a time. Our Sun is a third-generation star. It formed about 4.6 billion years ago from a cloud of gas and dust that had already been enriched by multiple previous generations of stellar death. And the atoms in your body, the carbon in your cells, the calcium in your bones, the iron in your blood, the oxygen in your lungs, were forged in those ancient stars and scattered through space by their deaths before gravity gathered them into the nebula that became our solar system. We are, quite literally, made of stardust, not metaphorically, not poetically, physically. The atoms inside you right now were once part of stars that burned and died billions of years before our Sun existed. You are the universe looking at itself. You are ancient starlight, rearranged by 4 billion years of biology, sitting in a room and watching a video about the cold of space. That is not something to gloss over. That deserves a moment. Now, back to temperature. Because the universe's cooling story isn't finished, not by a long way. The universe today, as we said, sits at 2.7 Kelvin on average in deep space. But that average is deceiving because the universe is extraordinarily lumpy. There are places of tremendous heat, the cores of stars, the accretion disks around black holes, the sites of supernova explosions, and vast regions of cold. The contrast is enormous. The Sun's core burns at around 15 million degrees Celsius. Its surface, by comparison, is a relatively cool 5,500 degrees Celsius, though that's still hot enough to vaporize steel in seconds. And around certain neutron stars and black holes, temperatures in the surrounding gas can reach hundreds of millions of degrees, but the spaces between galaxies, the cosmic voids, the vast empty regions that make up most of the universe's volume, are cold, tenuous, sparsely filled with stray atoms and the ever-present wash of the CMB. And here is something that should blow your mind. The universe is still expanding. Not just expanding, accelerating. The expansion is speeding up, driven by a mysterious force or property of space itself that we call dark energy. We don't know what dark energy is. We know it exists because we can measure its effects on the expansion of the universe. We know it makes up roughly 68% of the total energy content of the universe. But its fundamental nature, still one of the deepest open questions in all of physics. What dark energy means for temperature is profound. As the universe expands, the CMB continues to cool. Right now it sits at 2.7 Kelvin. In a trillion years, a number 1,000 times larger than the current age of the universe, it will have cooled far further. The universe will be darker, emptier, colder, and if you follow the math out far enough, you arrive at one of the most haunting concepts in cosmology, the heat death of the universe. The heat death, despite its name, is about cold, not heat. It describes the theoretical final state of a universe that has reached maximum entropy, a universe where every star has burned out, where every black hole has eventually evaporated through a quantum process called Hawking radiation, where matter itself may have decayed into its most elementary components, where there are no more temperature differences anywhere, no gradients, no hotspots, no cold regions. just an unimaginably vast, unimaginably cold, nearly featureless sea of photons and elementary particles spread evenly across a cosmos that has grown so large that even light can barely cross it in any meaningful time. The temperature of this final state, effectively zero, as close to absolute zero as the universe will ever reach. Not quite there. The third law of thermodynamics still holds, but asymptotically approaching it over timescales that make our 13.8 billion-year-old universe look like the opening sentence of an infinitely long novel. We're talking about timescales measured in numbers like 10 to the power of 100 years, or 10 to the power of 1,000 years, numbers that have no real-world anchor, numbers that exist only in the equations of cosmologists and the imaginations of people willing to follow physics to its absolute extreme. The universe began in a fireball of incomprehensible heat, and it will end, if end is even the right word, in a cold, dark, silent stillness almost indistinguishable from nothing at all. And yet, between that fiery beginning and that quiet end, there was a moment, a brief, dazzling, cosmically improbable moment, when the conditions were just right for stars to form, for planets to cool, for oceans to gather, for life to emerge, for brains to develop the capacity to ask questions about the universe that made them. We are living in that moment, right now, in the middle of cosmic history, in the brief, warmly lit chapter between the fire and the cold. Doesn't that make you want to look up? But here's what most people don't realize, and this is where our next chapter takes us. The cold of space isn't just a background fact. It has direct, measurable, sometimes devastating consequences for anything that dares to venture into it. Spacecraft, telescopes, hypothetical human missions to the outer solar system and beyond, and the engineers who design space missions lose sleep over temperature. Because out there, keeping things warm enough or cool enough is one of the hardest engineering challenges in all of space exploration. If you are enjoying this journey, make sure to give this video a like and subscribe. In this channel, we explore the cosmos together, and you do not want to miss what's coming up on this channel over the next few months. Engineering is, at its heart, the art of solving problems that nature never intended to be solved. And space? Space is nature's ultimate problem statement. Every mission we've ever sent beyond Earth's atmosphere has had to wrestle with temperature in ways that most people never think about. Not just the cold, though the cold is relentless and punishing, but the wild, swinging extremes, the difference between blazing heat and absolute frigidity that can occur within the span of a few minutes as a spacecraft moves from sunlight into shadow. The challenge of keeping sensitive electronics warm enough to function, while simultaneously keeping other components cool enough not to overheat. It's a balancing act performed across millions of kilometers, with no margin for error and no possibility of a repair crew showing up if something goes wrong. Let's start with a spacecraft that many people know by name but few people fully appreciate, Voyager 1. Launched in September of 1977, that's nearly half a century ago, Voyager 1 is the most distant human-made object in existence. As of today, it has traveled more than 23 billion kilometers from Earth. It is so far away that a radio signal traveling at the speed of light takes over 22 hours to reach it, over 22 hours, one way. And it is still functioning. Think about that for a moment. A spacecraft built in the early 1970s, using technology that predates personal computers, that predates the internet, that predates virtually every piece of technology you interact with on a daily basis, is still alive, still sending data back to Earth from a distance that staggers the imagination. How? One of the key answers is heat. Voyager 1 carries something called a radioisotope thermoelectric generator, or RTG. It's essentially a nuclear battery. Inside it, plutonium-238 undergoes radioactive decay, releasing heat as it does so. That heat is converted into electricity using a device called a thermoelectric converter. No moving parts, no pumps, no turbines. Just the direct conversion of heat into electrical current through a principle discovered in the early 19th century by a physicist named Thomas Johann Seebeck. The RTG does two things simultaneously. It generates the electricity that powers Voyager's instruments, and it generates waste heat that helps keep the spacecraft's interior warm enough for the electronics to function in the -200+ degree environment of deep space. As the plutonium decays, it produces less and less heat over time. The power output of Voyager's RTG has been declining by roughly 4 watts per year. Engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, have been carefully managing this decline for decades, turning off instruments one by one as power becomes scarcer, making agonizing choices about which scientific measurements are worth the energy cost. Even now, the team continues to find ways to squeeze more life out of a spacecraft that was designed for a 5-year mission and has now been flying for nearly 5 decades. It's one of the most extraordinary feats of engineering management in human history, and it all comes back to this fundamental challenge: keeping things warm enough to work in the cold of space. Now let's talk about a very different approach to temperature management, one that goes in the exact opposite direction, because while Voyager needs warmth to survive, some of our most powerful scientific instruments need cold, extreme cold, cold that rivals the Boomerang Nebula, cold that approaches the lowest temperatures ever achieved in a laboratory. The James Webb Space Telescope, launched on the 25th of December 2021, Christmas Day, Webb is the largest, most powerful space telescope ever deployed. It sits at a location called the Second Lagrange Point, or L2, about 1.5 million kilometers from Earth, in the direction away from the Sun. It orbits this point in a kind of perpetual gravitational dance that keeps it roughly in line with Earth as our planet moves around the Sun. Webb's mission is to see the universe in infrared light, not visible light like our eyes detect. Infrared heat radiation, the kind of light emitted by cool objects by distant galaxies whose light has been redshifted by the expansion of the universe, by the atmospheres of exoplanets, by the dusty cocoons of newborn stars. And here's the fundamental challenge with an infrared telescope: everything that has temperature emits infrared radiation. Everything. Including the telescope itself, including the mirrors, including the detectors. If the telescope were anywhere near room temperature, it would be blinded by its own heat, like trying to look at a candle flame while standing inside a bonfire. To see the cold, faint infrared light of the distant universe, the telescope has to be cold, extraordinarily cold. Webb achieves this in 2 ways. First, it has a sun shield, an enormous 5-layered tennis court-sized barrier made of a material called kapton, coated with reflective aluminum and silicon. This sun shield blocks the heat and light of the Sun, Earth and Moon simultaneously, keeping them from reaching the telescope's mirrors and instruments. The sun shield is so effective that the temperature difference between its sun-facing side and its cold side is staggering. The hot side reaches temperatures of around 110 degrees Celsius. The cold side drops to around -233 degrees Celsius. That's a temperature difference of over 340 degrees across a structure just a few millimeters thick in places. But even that extraordinary cold isn't enough for Webb's most sensitive instrument. The mid-infrared instrument, called MIRI, needs to operate at -266 degrees Celsius. That is just 7 degrees above absolute zero. 7. To achieve that, MIRI uses an active cooling system, a mechanical refrigerator called a pulse tube cooler combined with a Joule-Thomson heat exchanger. Compressed helium gas is cycled through the system, expanding and contracting in a precisely controlled rhythm, each cycle pulling a tiny amount of heat away from Miri and dumping it elsewhere. It's a miniaturized version of the same principle behind your home refrigerator, engineered to work flawlessly in space, operating without maintenance in a vacuum for what engineers hope will be a mission lasting well over a decade. The result is a detector so cold, so quiet, so exquisitely sensitive that it can detect infrared signals from galaxies over 13 billion light-years away. It can analyze the atmospheres of planets orbiting other stars, looking for water vapor, carbon dioxide, methane, and other molecules that might hint at the possibility of life. It can peer through the dust clouds that hide newborn stars and see the protoplanetary disks where new worlds are forming right now. All of this because someone figured out how to make something colder than almost anything else in the natural universe. Cold, it turns out, isn't just an obstacle in space exploration. It's also one of our most powerful tools. Let's talk about some other missions and what they've taught us about temperature in space. The Cassini spacecraft, which spent 13 years orbiting Saturn before its intentional plunge into the planet's atmosphere in September of 2017, had to manage temperatures ranging from the relative warmth near the inner solar system during its journey to the cold of the Saturnian system, roughly 1.4 billion kilometers from the Sun on average. Saturn's moon Titan, the only moon in the solar system with a dense atmosphere, has surface temperatures around -179 degrees Celsius, cold enough that methane exists there as a liquid. Titan has lakes and rivers and rain and weather just like Earth, but instead of water, the working fluid is methane. Lakes of liquid methane sit on its surface, fed by methane rain falling from orange hydrocarbon clouds. Cassini discovered these methane lakes with its radar instrument, and later missions are being planned to explore them more directly. NASA's Dragonfly mission, a rotorcraft lander designed to fly through Titan's thick atmosphere, is currently in development and aims to reach Titan in the mid-2030s. It will land on a world where the temperature never rises above roughly -179 degrees Celsius, where breathing the atmosphere would be immediately fatal, where the sky is a perpetual orange haze, and where the rivers and seas are filled not with water, but with liquid natural gas. And yet even there, some scientists believe the conditions might not be entirely hostile to some form of life. Not life as we know it, not life based on liquid water and carbon chemistry at comfortable temperatures, but perhaps a radically different kind of life, life based on liquid methane as a solvent, life with chemistry that operates at temperatures a human being would find lethally cold. We don't know. We haven't found it. But the fact that we can seriously ask the question, that the boundaries of what we consider possible for life have been pushed outward by what we've discovered about extreme environments, is one of the most exciting developments in modern astrobiology. Now, one of the most fascinating temperature-related discoveries in recent solar system exploration comes from a place you might not expect: the Moon, our Moon, the one that has been orbiting Earth for about 4.5 billion years, the one humans have walked on, the one we know so well, or think we know so well. In 2020, NASA's Stratospheric Observatory for Infrared Astronomy, SOFIA, a modified Boeing 747 aircraft carrying a telescope, confirmed something extraordinary. Water ice exists on the sunlit surface of the Moon, not just in the permanently shadowed craters near the poles, where ice has been suspected for decades, but in small pockets on the sunny side of the Moon as well, hiding in the shadows of tiny surface features in regions that never quite get warm enough to evaporate the ice. And those permanently shadowed polar craters, they are some of the coldest places in the entire solar system, not just cold by Earth standards. Some of these craters at the lunar South Pole have never, in billions of years, been touched by sunlight. Their temperatures have been measured at around -240 degrees Celsius, colder than most places in the outer solar system, colder than the surface of Pluto in some cases. Because they have no atmosphere to trap or move heat, and no sunlight to warm them, these craters have essentially been sitting at near constant temperature since they formed. They are cold traps. Any volatile material that drifts into them gets frozen and stays frozen, potentially for billions of years. This makes them scientifically priceless. The ice and frozen gases locked in these craters may be ancient cometary material delivered to the moon billions of years ago, a frozen record of the early solar system preserved in the cold. And from a practical standpoint, if humans are to establish a permanent presence on the moon, as NASA's Artemis program aims to do in the coming years, that water ice is a critical resource. It can be melted for drinking water, split into hydrogen and oxygen for rocket fuel, used for radiation shielding. The cold of the moon, which seems at first like purely an obstacle, turns out to be one of the moon's most valuable features. It's remarkable, isn't it, how consistently this theme appears. Cold as obstacle, cold as tool, cold as record keeper, cold as the very condition that makes certain kinds of science, and perhaps certain kinds of life, possible. The universe's cold isn't a simple backdrop. It's an active force shaping the history of worlds, determining where water can exist, dictating the design of every spacecraft we build, influencing the chemistry of every moon and asteroid and comet in the solar system, and we've barely scratched the surface. Because there are places in the universe where the cold isn't just extreme, it's genuinely alien, where the physics of low temperature produces behaviors so strange, so counterintuitive, so thoroughly unlike anything in everyday experience, that they seem more like magic than science. And some of those behaviors, discovered first in laboratories on Earth, are now believed to occur naturally in the cosmos. We're talking about superfluids, superconductors, Bose-Einstein condensates, states of matter that only exist at the edge of absolute zero, where quantum mechanics stops being a background detail and becomes the dominant reality. There is a temperature at which matter stops behaving like matter, not in the sense that it disappears, not in the sense that it transforms into energy or ceases to exist, but in the sense that the rules governing its behavior, the rules you learned in school, the rules that describe how liquids flow and solids hold their shape and gases expand, those rules quietly break down, and something else takes over, something deeper, something that lives underneath the ordinary physics of everyday life, waiting patiently for the thermometer to drop far enough to let it out. That something is quantum mechanics, and when temperature falls toward absolute zero, quantum mechanics doesn't just become relevant, it becomes everything. Let's start with something discovered over a century ago, because the history here is as fascinating as the physics. In 1911, a Dutch physicist named Heike Kamerlingh Onnes was doing something that almost no one else in the world could do at the time. He was cooling materials to temperatures close to absolute zero, using liquid helium that he had figured out how to produce in his laboratory in Leiden. The first person in history to successfully liquefy helium back in 1908. Onnes was measuring the electrical resistance of mercury as it cooled. Resistance is the property that makes wires heat up when current flows through them. It's essentially how much a material fights the flow of electrons. Every material has it. Even the best conductors, like copper and silver, have some resistance, which is why power lines lose energy over long distances and why the filament in an old-fashioned light bulb glows with heat. As Onnes cooled the mercury, he watched the resistance drop as expected. Cold materials generally conduct electricity better than hot ones, but then, at around 4.2 Kelvin, just 4.2 degrees above absolute zero, Something happened that he did not expect at all. The resistance didn't just get lower, it vanished completely, entirely, to zero. Not close to zero, not so small it was hard to measure, zero. The mercury had become a perfect conductor of electricity, a material through which electrical current could flow forever without losing any energy at all. Ons called it superconductivity, and it won him the Nobel Prize in Physics in 1913. What causes superconductivity is a quantum mechanical phenomenon. In a normal metal, electrons moving through the material constantly bump into vibrating atoms, losing energy with each collision. That's resistance. But below a critical temperature, something extraordinary happens. Electrons begin to pair up. Two electrons, which ordinarily repel each other because they carry the same negative charge, form what are called Cooper pairs, mediated by subtle interactions with the vibrating atomic lattice. And these Cooper pairs behave differently from individual electrons in a profound way. They become quantum mechanically coherent. They synchronize. They stop being individual particles bouncing around independently and start behaving as a single collective quantum entity, a wave that flows through the material without scattering, without losing energy, without resistance. It's one of the most counterintuitive things in all of physics. Two particles that repel each other forming a bond. A material that becomes a better conductor not through engineering or purity, but simply by getting cold enough for quantum effects to dominate. Superconductivity has enormous practical applications here on Earth. It's used in the powerful magnets inside MRI machines in hospitals, in particle accelerators like the Large Hadron Collider at CERN in Switzerland, in experimental power transmission lines, and in emerging quantum computing systems. But what we want to ask today is the cosmic question: does superconductivity exist anywhere in the universe naturally? The answer is almost certainly yes, neutron stars. Neutron stars are among the most extreme objects in the known universe. They form when a massive star, roughly 8 to 20 times the mass of our Sun, reaches the end of its life and its core collapses in a supernova explosion. The collapse is so violent, so catastrophically fast, that protons and electrons are forced together, merging to form neutrons. The result is an object roughly 1.4 times the mass of our Sun, compressed into a sphere only about 20 kilometers across. 20 kilometers. You could drive across a neutron star in about 12 minutes if driving on the surface of a neutron star weren't instantly and spectacularly fatal. The density is incomprehensible. A teaspoon of neutron star material would weigh roughly 400 million tons on Earth. The gravity on the surface is around 200 billion times stronger than what you feel standing here. The magnetic fields of some neutron stars, called magnetars, are so powerful that they would disrupt the electrons in your body from a distance of 1,000 kilometers now. The surface of a neutron star, right after it forms in a supernova explosion, is extraordinarily hot. We're talking about temperatures of around 100 billion Kelvin in the immediate aftermath. But neutron stars cool rapidly, astrophysically speaking, and within about 1 million years, their surface temperatures drop to something in the range of 100,000 to 1 million Kelvin. Still unimaginably hot by human standards, but cool by neutron star standards, and the interior of a mature neutron star, deep inside, where the density is highest and the quantum effects most extreme. Physicists believe that the neutrons themselves may form Cooper pairs, just like the electrons in a superconductor, and flow without friction in a state called a neutron superfluid. A superfluid is like a superconductor, but instead of electrons flowing without electrical resistance, a liquid flows without any viscosity at all. Zero friction, perfect lossless flow. The implications of neutron superfluidity inside neutron stars are profound. It may explain a phenomenon called a pulsar glitch. a sudden, tiny but detectable spin-up in the rotation rate of pulsars, which are rapidly rotating neutron stars that emit beams of radio waves with extraordinary clock-like regularity. When a pulsar glitches, its rotation rate suddenly increases by a tiny fraction, then slowly relaxes back. The leading explanation involves the superfluid interior of the neutron star suddenly coupling to the outer crust, transferring angular momentum, a kind of quantum mechanical hiccup in an object smaller than a city but more massive than the Sun. We're detecting quantum behavior inside objects 13 billion kilometers away, and we're doing it by listening to the ticking of a cosmic clock. Now let's talk about something even stranger. In 1995, using techniques that had been theorized for decades but never quite achieved, physicists Eric Cornell and Carl Wieman at the University of Colorado in Boulder, working with a gas of rubidium atoms, cooled their sample to about 170 nanokelvin, 170 billionths of a degree above absolute zero, and at that temperature, something happened that Albert Einstein and Satyendra Nath Bose had predicted mathematically back in 1924 and 1925, but that no one had ever actually seen. The atoms stopped being individual particles. Their quantum wave functions, the mathematical descriptions of their positions and behaviors, spread out and overlapped. And when they overlapped, they merged. The entire collection of atoms collapsed into a single quantum state, behaving as one unified quantum object rather than a collection of individuals. Every atom in the sample was simultaneously in the same place, doing the same thing, described by a single wave function. This new state of matter was called a Bose-Einstein condensate, named for the two physicists who predicted it 7 decades earlier, Cornell and Wieman, along with Wolfgang Ketterle at MIT, who independently achieved the same result shortly afterward, shared the Nobel Prize in Physics in 2001. A Bose-Einstein condensate is not a solid, not a liquid, not a gas, not a plasma. It is a fifth state of matter, and it behaves in ways that are genuinely alien to everyday experience. It flows without any friction whatsoever, forming a perfect superfluid. If you put it in a container and set it spinning, it will spin forever, no friction to slow it down. If you try to stir it, it will form tiny quantum vortices, little tornadoes of quantized rotation that are a direct signature of the underlying quantum nature of the state. In the laboratory, Bose-Einstein condensates are extraordinarily fragile. They exist only in conditions of near-perfect isolation. The slightest vibration, the faintest stray photon, the merest hint of thermal energy from the surroundings, and the condensate falls apart. Maintaining them requires some of the most sophisticated experimental setups in all of physics. But the cosmos doesn't always play by the same rules as a laboratory. Some theoretical physicists have proposed that under the right conditions, in the incredibly dense interiors of neutron stars, or possibly in certain exotic dark matter scenarios, Bose-Einstein condensate-like states might form naturally. The mathematics isn't fully settled, and these remain theoretical proposals rather than confirmed observations. But the idea that the universe's most exotic quantum states of matter might be sitting inside the densest objects in the cosmos, hidden from our direct view but influencing the behavior of things we can observe, is one of the most tantalizing possibilities in modern theoretical astrophysics. And then there is helium. Ordinary helium, helium-4, the kind released from party balloons, becomes a liquid at 4.2 Kelvin at normal atmospheric pressure. Cool it further to 2.17 Kelvin, and something remarkable happens. It becomes a superfluid. It flows up and over the walls of containers. It seeps through microscopic cracks that no normal liquid could pass through. It conducts heat with essentially perfect efficiency. If you spin a container full of superfluid helium and then stop the container, the helium keeps rotating indefinitely because there's no friction to stop it. Superfluid helium was first discovered in the late 1930s, and it has been one of the most important tools in low-temperature physics ever since. The cooling system on the James Webb Space Telescope that we talked about earlier uses helium, specifically helium-3, a rarer isotope, as part of its cooling chain. Even the cosmic engineering of our most sophisticated telescopes relies on the quantum behavior of one of the universe's most abundant elements. Helium, incidentally, is the second most abundant element in the universe. It makes up roughly 24% of all the ordinary matter in the cosmos by mass. Almost all of it produced in those first 3 minutes after the Big Bang, during the nucleosynthesis we talked about. Every helium atom in every balloon, in every star, in every cooling system of every space telescope was made in the first few minutes of the universe's existence. We are surrounded by relics of the Big Bang. We are using them to explore the universe. There is something profoundly circular and beautiful about that. Let's pull back for a moment and think about what all of this tells us. We started this part of our journey with Onnes cooling mercury in his laboratory in Leiden, watching electrical resistance disappear, discovering something that seemed almost magical. From that moment, just over 100 years ago, a chain of discovery unfolded that led us to Cooper pairs, to neutron superfluids, to Bose-Einstein condensates, to the cooling systems of the most powerful telescope ever built, to theories about the quantum interiors of objects 16,000 light-years away, all of it connected, all of it flowing from one simple act of curiosity, cooling something down and watching what happens. This is what science actually looks like, by the way. Not a rigid march from question to answer. Not a clean, straight line from ignorance to knowledge, but a web. An expanding, interconnected web of ideas and experiments and surprises, where a discovery made in a laboratory in the Netherlands ripples outward across a century and touches the design of a telescope orbiting the Sun, and the theoretical interior of a spinning stellar remnant, and the quantum nature of matter itself. Every time someone told us the universe was fully understood, it turned out we had barely begun. And here's the beautiful thing. Here's the thing that should make you genuinely excited, not just intellectually curious, but viscerally, personally excited. We are still at the beginning. The questions we don't yet know how to ask outnumber the ones we've answered. The phenomena we haven't discovered yet are, by definition, invisible to us right now. And somewhere out there, perhaps in the career of someone watching this video right now, perhaps in an experiment being designed at this very moment in a university laboratory somewhere on this planet, the next Onnes moment is waiting, the next impossible observation, the next result that makes physicists look at each other across a room and say, that can't be right, and then spend the next 50 years proving that it is. But there's one more dimension of cold in space that we haven't touched on yet. One that feels more personal, more immediate, more directly connected to the question of what space exploration actually means for human beings. What happens to the human body in the cold of space? Not in a general sense, not the physics of heat transfer and radiation we covered in part 1, but specifically, concretely, biologically, what does extreme cold do to living tissue? What are the actual mechanisms? And what is our species doing right now in real ongoing research to address the challenge of keeping humans alive on long journeys through the cold dark between the worlds? Let's get personal. Because everything we've talked about so far, the cosmic background radiation, the quantum states of matter, the engineering of telescopes and deep space probes, all of it exists at a comfortable intellectual distance, fascinating, awe-inspiring, but ultimately about things out there, things beyond us. But you are made of matter. You are a biological system, a remarkably fragile, remarkably complex, remarkably temperature-dependent biological system. And if you were ever placed in the environment we've been describing, the genuine cold of deep space, your body would respond in ways that are both deeply understood and, at the frontier of current research, still profoundly mysterious. So let's talk about what cold actually does to a living human being. And then let's talk about what that means for the future of human spaceflight. Your body right now is maintaining a core temperature of approximately 37 degrees Celsius, give or take half a degree. This isn't an accident or a preference, it is a biological imperative. Every enzyme in your body, every protein machine that drives your metabolism, copies your DNA, powers your muscles, transmits signals across your neurons, evolved to function within a narrow temperature window centered on that 37-degree mark. Drop your core temperature by just 2 degrees to 35, and you begin experiencing mild hypothermia. Shivering intensifies, your fine motor skills degrade, thinking slows. Your body is already redirecting blood flow away from your extremities, your fingers, toes, nose, ears, toward your core, trying to protect your vital organs at the expense of everything else. Drop to 32 degrees and the shivering paradoxically stops. Your body gives up on that energy-expensive strategy. Confusion deepens, muscle coordination deteriorates significantly. You may begin making strange decisions. People in advanced hypothermia sometimes remove their clothing, a phenomenon called paradoxical undressing, because confused nerve signals create a false sensation of heat. At 28 degrees core temperature, your heart becomes dangerously unstable. Cardiac arrhythmias, irregular heartbeats become likely. Consciousness fades. Below 20 degrees, the heart typically stops, a drop of just 17 degrees from normal body temperature. 17 degrees is the difference between a perfectly healthy human being and a stopped heart. In a universe where temperatures range from 142 nonillion Kelvin down to fractions of a degree above absolute zero, a range spanning more than 32 orders of magnitude, the window in which human life can exist is astonishingly, almost absurdly narrow. We are fragile things, pretending to explore an environment that was never built with us in mind. Now, here's something counterintuitive that medicine has known about for decades. Extreme cold can also save lives. Therapeutic hypothermia, the deliberate controlled cooling of a patient's body, is an established medical technique used after cardiac arrest and certain types of stroke. When the brain is deprived of oxygen, the damage doesn't happen entirely in the moment of deprivation. A significant portion of the damage occurs in the minutes and hours afterward, as oxygen-starved cells trigger a cascade of chemical reactions that spread destruction far beyond the initial injury zone. Cooling the brain slows this cascade. Every degree of temperature reduction cuts the metabolic rate of brain tissue, buying precious time. Patients cooled to around 32 to 34 degrees Celsius after cardiac arrest have been shown in clinical trials to have significantly better neurological outcomes than patients kept at normal body temperature. The body's vulnerability to cold and its potential salvation through cold turn out to be two sides of the same coin. And this observation, that cold slows biological processes dramatically, sits at the heart of one of the most ambitious and scientifically serious research programs in modern space medicine, human hibernation. The idea of putting astronauts into some form of suspended animation for long space voyages has been a staple of science fiction for decades. From the crew of the Discovery in Stanley Kubrick's 2001, A Space Odyssey, to the colonists in Ridley Scott's Aliens, to the passengers in the film Passengers, the image of human beings sleeping their way across interstellar distances is deeply embedded in our cultural imagination of space travel. But how close are we to actually doing it? Closer than most people realize, and further than the science fiction suggests, both things at the same time. The most serious scientific work in this area focuses not on deep, indefinite suspended animation, but on something more modest and more achievable, a state called torpor. Torpor is a natural biological phenomenon. Many mammals do it: bears during winter hibernation, ground squirrels, which can drop their body temperature to just above freezing for weeks at a time, lemurs in Madagascar, certain species of bats, even some birds. During torpor, metabolic rate drops dramatically, sometimes to just 5% of normal. Heart rate slows from dozens of beats per minute to just a few. Core temperature falls significantly. The animal becomes unresponsive to most stimuli, and crucially, this is the part that researchers find most exciting: the animal emerges from torpor without lasting damage. Its organs haven't failed. Its muscles haven't completely wasted away. Its brain works. In 2019, researchers at the Salk Institute for Biological Studies in California identified what they believe is the neural circuit responsible for triggering torpor-like states in mice, animals that don't naturally hibernate. By activating specific neurons in the hypothalamus, they could induce a torpor-like state in mice, causing their body temperature and metabolic rate to drop significantly. The mice recovered fully when the stimulation ended. This was a landmark result. It suggested that the biological machinery for torpor might be present in mammals broadly, including potentially in humans. That we might not need to engineer something entirely new. We might just need to find the right switch. A company called SpaceWorks Enterprises has been working with NASA on concepts for torpor-inducing systems for long-duration spaceflight. Their designs involve cooling astronauts to around 32 degrees Celsius, mild hypothermia, using a technique already used in hospitals called nasopharyngeal cooling, where cool liquid is circulated through the nasal passages to bring the brain temperature down gently. Astronauts would be fed intravenously, have their muscles stimulated electrically to prevent significant atrophy, and rotate through cycles of torpor and wakefulness over the course of a long mission. The projected benefits are substantial: reduced food and water consumption, reduced psychological stress from the isolation and confinement of long spaceflight, reduced radiation exposure because a body in torpor may have some enhanced cellular repair capacity, and significantly reduced spacecraft mass, because you need far fewer supplies for sleeping passengers than for active ones. None of this is operational yet. The challenges are real and significant. Humans don't have the same genetic adaptations that allow ground squirrels to survive weeks at near-freezing temperatures without organ damage. The biochemistry of natural mammalian hibernators involves numerous protective mechanisms, elevated antioxidants, modified protein chemistry, specific hormonal changes that we don't yet fully understand or know how to replicate pharmacologically. But the research is serious, the funding is real, and the trajectory of the science is encouraging. There's another dimension of the cold problem in long-duration spaceflight that doesn't get nearly enough attention. Radiation deep space is not just cold. It is saturated with ionizing radiation, cosmic rays, solar energetic particles, trapped radiation belts around planets. Earth's magnetic field and atmosphere protect us from most of this on the surface. Low Earth orbit, where the International Space Station flies, is partially protected by Earth's magnetosphere, but go beyond that protective bubble and the radiation environment changes dramatically. On the surface of Mars, with no global magnetic field and a very thin atmosphere, radiation doses would be roughly 17 times higher than on Earth's surface. On a deep space transit to Mars, a journey of roughly 6 to 9 months each way, depending on the trajectory, astronauts would receive radiation doses significantly above what NASA currently considers acceptable career limits. And the connection to cold? Some of the most promising radiation shielding concepts involve water. Because hydrogen atoms are remarkably effective at absorbing and scattering high-energy particles, and the most mass-efficient way to carry water on a long voyage might be in a frozen state. Ice walls surrounding the crew quarters, doing double duty as radiation shielding and water reserve. The cold that threatens life also becomes, in this configuration, part of the architecture of survival. Furthermore, several research groups are investigating whether certain organisms known as extremophiles, life forms that thrive in conditions lethal to most biology, might offer insights into radiation resistance. Organisms like Deinococcus radiodurans, a bacterium capable of surviving radiation doses thousands of times higher than those that would kill a human being, achieve this partly through extraordinarily efficient DNA repair mechanisms. Understanding how it does this and whether any of those mechanisms could be artificially enhanced in human cells is an active area of astrobiology and space medicine research. Let me tell you about someone who has experienced the cold of space more directly than almost any other human being alive, Scott Kelly. Scott Kelly is a retired NASA astronaut who spent 340 consecutive days aboard the International Space Station from March 2015 to March 2016, at the time, the longest single spaceflight by an American astronaut. His identical twin brother Mark remained on Earth throughout, serving as a biological control subject in what became one of the most extraordinary human biology experiments ever conducted. The NASA Twin Study, as it became known, compared the brothers' biology before, during, and after Scott's mission. The results, published in the journal Science in 2019, were illuminating and occasionally surprising. Scott's gut microbiome changed significantly. His cognitive performance showed some decline in certain tests. His gene expression, the pattern of which genes were active at any given time, shifted in hundreds of ways compared to his Earth-based brother. His telomeres, the protective caps on the ends of chromosomes, whose length is often used as a marker of cellular aging, actually lengthened during the mission, which was unexpected and is still not fully understood. Upon return, most of the changes reverted toward pre-flight baselines, but not all of them, and not at the same rate. Long-duration spaceflight changes the human body in ways we are still cataloging and beginning to understand. The cold is part of that environment. The spacecraft's thermal management systems work continuously to maintain livable temperatures inside, while the outside environment sits at -270 degrees, but so is the radiation, the microgravity, the confinement, the disrupted circadian rhythms, the psychological weight of isolation. Keeping a human being alive and healthy in space is not a single engineering problem. It's dozens of interacting problems, all influencing each other, all requiring simultaneous solutions. And the further we go, the deeper into cold and dark and radiation we venture, the harder those problems become, which brings us to the most extreme version of the question: what would it actually take to send a human being to another star? Not Mars, not the outer solar system, another star. Proxima Centauri, the closest star to our Sun, sits 4.24 light-years away. At the speed of our fastest current spacecraft, the Parker Solar Probe has reached speeds of around 693,000 kilometers per hour at its closest approach to the Sun, making it the fastest human-made object ever. A journey to Proxima Centauri would take roughly 6,900 years. 6,900 years. Civilizations have risen and fallen in less time than that. The pyramids at Giza are only about 4,500 years old. To make interstellar travel remotely conceivable within human timescales, we would need either a dramatically different propulsion technology, something capable of reaching a substantial fraction of the speed of light, or a way of managing the passage of time for the travelers themselves, through hibernation, through generation ships, where the original traveler's descendants complete the journey, or through some technology we don't yet possess. The cold of interstellar space, that unrelenting 2.7 Kelvin environment bathed in cosmic radiation, utterly absent of any warmth or sustenance, would be the backdrop against which any such journey would unfold. A journey through a medium that is, in every meaningful physical sense, as hostile to human life as any environment we can imagine. And yet, people are thinking about this seriously. Physicists, engineers, biologists, ethicists. The Breakthrough Starshot Initiative, announced in 2016 and backed by significant funding, proposed sending tiny laser-propelled probes, centimeter-scale spacecraft driven by an enormously powerful ground-based laser array, to Proxima Centauri at roughly 20% of the speed of light. Such a probe could reach the nearest star in about 20 years, no humans on board, just sensors, just cameras, but the ambition is real, and the physics, while enormously challenging, doesn't violate anything we know about how the universe works. We are, as a species, beginning to seriously contemplate reaching out to the stars. And the cold that fills the space between them, the cold we've been exploring together throughout this video, is not just an obstacle. It's a measure of the distance, a reminder of the scale of what we're attempting, and somehow, in a way that's hard to fully articulate but easy to feel, a reminder of why it matters that we try. Because we are the universe trying to understand itself. We are ancient stardust that somehow learned to wonder, and the cold darkness between the stars isn't our enemy, it's our invitation. If you're still watching, your mind works the way this channel was built for. Don't forget to subscribe and give this a like. Every video we ask the questions most people are afraid to sit with, and we go all the way to the answer, step back, way back, further than we've gone before, further than our solar system, further than our galaxy, further than the local group of galaxies that surrounds us. Pull your perspective outward until the Milky Way, a structure containing somewhere between 100 billion and 400 billion stars, spanning roughly 100,000 light-years across, shrinks to a faint smudge, then keep going until even that smudge disappears into a larger pattern. Because when you look at the universe at its largest scales, scales of hundreds of millions and billions of light-years, something extraordinary comes into view, something that no individual star or galaxy or even galaxy cluster hints at. A structure so vast, so intricate, and so beautiful that the first time most people truly grasp it, it stops them cold. The cosmic web. The universe at its largest scales is not a uniform sea of matter. It is not a random scatter of galaxies distributed evenly through space. It is a web, an enormous three-dimensional network of filaments, long, thread-like structures of gas and dark matter and galaxies, stretched between vast, nearly empty regions called cosmic voids. The filaments are where most of the ordinary matter in the universe lives, where gas flows and condenses and feeds the formation of galaxies, where galaxy clusters, the largest gravitationally bound structures in the universe, containing hundreds or thousands of individual galaxies, sit at the intersections like cities at the crossroads of ancient trade routes. And the voids? The voids are something else entirely. Cosmic voids are the spaces between the filaments, regions where the density of matter is dramatically lower than the cosmic average. Some voids span hundreds of millions of light-years. The Bootis void, one of the largest known, stretches approximately 330 million light-years across. If our Milky Way were located at the center of the Bootis void, we would not have discovered that other galaxies existed until the 1990s, because the nearest galaxies would have been so far away that the technology to detect them at that distance simply didn't exist until then. 330 million light-years of almost nothing. These voids are not completely empty. There are some galaxies in them, lonelier, more isolated galaxies than anything we see in the filaments and clusters, and they are filled with the cosmic background radiation, that ever-present 2.7 Kelvin glow, and with stray gas and dark matter thinly spread. But their density is roughly 20% of the cosmic average. In a universe that is itself mostly empty, the voids are the emptiest places of all, and they are cold, not dramatically colder than the average temperature of deep space. The CMB fills them too, after all. But the temperature of the gas in cosmic voids, the actual baryonic matter, the protons and electrons and atoms, is among the lowest for any gas in the universe. Some void regions contain gas at temperatures of only a few thousand Kelvin, extraordinarily hot by human standards, but among the coldest diffuse gas known in the cosmos, because it is so isolated from the heat sources that warm gas elsewhere, no nearby galaxies with their active star formation and supernova explosions, no galaxy clusters with their hot intracluster medium, just thin, cold, ancient gas floating in the dark between the great structures of the universe. Now let's talk about the gas that does sit in galaxy clusters. Because here, at the opposite end of the spectrum, we find some of the hottest ordinary matter in the universe. Galaxy clusters, massive gravitational collections of hundreds to thousands of galaxies, along with enormous amounts of dark matter and hot gas, contain what's called the intracluster medium. This is a diffuse plasma of gas that fills the space between the individual galaxies within the cluster. And it is extraordinarily hot. We're talking about temperatures ranging from 10 million to 100 million degrees Celsius. Temperatures so high that the gas emits primarily in X-rays, far beyond the visible spectrum. To see this gas, you need X-ray telescopes, and over the past few decades, missions like NASA's Chandra X-ray Observatory, launched in July of 1999 and still operating, and ESA's XMM Newton, launched in December of 1999, have mapped this superheated gas in extraordinary detail. Why is it so hot? Several reasons. When matter falls into the deep gravitational well of a galaxy cluster, it accelerates. When it collides with other infalling matter, that kinetic energy converts to heat. Galaxy clusters are the sites of some of the most energetic collisions in the universe. When two clusters merge, the collision can release more energy than any other event since the Big Bang itself, and the gas in the merging clusters gets heated to extraordinary temperatures. One of the most spectacular examples is the Bullet cluster, actually two galaxy clusters that collided roughly 150 million years ago, located about 3.7 billion light-years from Earth. The collision was so energetic that the hot gas from each cluster was slowed by the impact. The gas clouds passed through each other imperfectly, interacting electromagnetically, heating even further and lagging behind the dark matter, which passed through the collision essentially unaffected. The Bullet cluster became one of the most direct and compelling pieces of evidence for the existence of dark matter, because astronomers could map where the mass was using gravitational lensing and show that it was not where the visible gas was. The mass was ahead of the gas, having passed through without interacting. Only something that doesn't interact electromagnetically, dark matter, could do that. Temperature, in this case, became a tool for understanding one of the universe's deepest mysteries. Speaking of dark matter, what is its temperature? This is a genuinely fascinating and still somewhat open question. Dark matter makes up roughly 27% of the total energy content of the universe, far more than ordinary matter, which accounts for only about 5%. We know it exists because of its gravitational effects. It shapes the rotation curves of galaxies. It forms the scaffolding of the cosmic web. Without it, galaxies as we know them could not have formed. The ordinary matter alone would not have clumped together quickly enough in the early universe to produce the structures we see today. But we don't know what dark matter actually is. We don't know what particle or particles make it up. And crucially, we don't know its temperature in the conventional sense, because dark matter doesn't appear to interact with electromagnetic radiation. It doesn't emit light, absorb light, or interact with photons at all. So measuring its temperature the way we measure the temperature of gas, by looking at the radiation it emits, doesn't work. What we can talk about is whether dark matter is hot or cold, in a specific technical sense that cosmologists use. Hot dark matter refers to particles that were moving at relativistic speeds, close to the speed of light in the early universe. Cold dark matter refers to particles that were moving slowly relative to the speed of light when they decoupled from the hot plasma of the early universe. This distinction matters enormously for the large-scale structure of the cosmos. Hot dark matter would have streamed freely through the early universe, smoothing out density fluctuations on small scales. In a universe dominated by hot dark matter, large structures, superclusters, filaments would form first and then fragment into smaller ones. Cold dark matter, by contrast, would clump on small scales first, building up larger structures hierarchically, small clumps merging into larger ones, those merging into still larger ones in a process called bottom-up structure formation. The cosmic web we observe, with its galaxies forming inside dark matter halos, those halos clustering into groups and clusters, those clustering into superclusters and filaments, matches the predictions of cold dark matter models far better than hot dark matter models. So while we don't know what cold dark matter is made of, we're fairly confident that it is cold in this specific cosmological sense, moving slowly, clumping effectively, providing the gravitational scaffolding around which ordinary matter assembled itself into everything we see. Cold dark matter is, in a very real sense, the skeleton of the universe. And the cosmic web, that magnificent large-scale structure we started this section with, is its visible fingerprint. Now let's look at the temperature map of the universe itself. Because one of the most powerful tools in modern cosmology is the ability to measure tiny temperature variations in the cosmic microwave background. Those ancient photons from 380,000 years after the Big Bang, with extraordinary precision. The CMB, as we discussed, has a nearly uniform temperature of 2.7 Kelvin everywhere you look. But nearly uniform is not exactly uniform. There are tiny fluctuations, temperature variations of about 1 part in 100,000 that encode an extraordinary amount of information about the early universe. These fluctuations were first mapped by the COBE satellite, the Cosmic Background Explorer, launched by NASA in November of 1989. The COBE team, led by George Smoot and John Mather, detected these tiny temperature anisotropies for the first time in 1992, confirming that the early universe had the small density variations needed to seed the formation of galaxies. Smoot and Mather shared the Nobel Prize in Physics in 2006. Then came WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001, which mapped the CMB with far greater resolution and precision. And then, most recently, the Planck satellite, launched by the European Space Agency in 2009 and operating until 2013, which produced the most detailed full-sky map of the CMB ever made. The Planck map is extraordinary. It shows the entire sky in microwave light, color-coded by temperature, with the tiny hot and cold spots, each representing a region of slightly higher or lower density in the early universe, laid out in extraordinary detail. From this map, cosmologists have been able to extract the age of the universe with remarkable precision: 13.8 billion years, the proportions of ordinary matter, dark matter, and dark energy, the geometry of space, whether it is flat, curved positively like a sphere, or curved negatively like a saddle, the spectrum of density fluctuations that seeded cosmic structure. All of this information encoded in temperature variations of 100,000th of a degree in the faint afterglow of creation. There is something almost miraculous about that. The universe wrote its autobiography in light, and we built instruments sensitive enough to read it. But there is a mystery in the CMB map that has troubled cosmologists for years. A region in the sky that, when you look at the temperature map carefully, seems anomalously cold. A spot called, somewhat dramatically, the cold spot, located in the direction of the constellation Eridanus in the southern sky. It covers a region of the sky roughly 5 degrees across, about 10 times the diameter of the full moon as seen from Earth, and it is colder than the surrounding CMB by about 70 microkelvins, 70 millionths of a degree, tiny by everyday standards but statistically significant in the context of CMB fluctuations. What causes it? Several explanations have been proposed. The most mundane is statistical. Perhaps it's simply a random fluctuation that our eyes, pattern-hungry as they are, have singled out for significance. In any large dataset, extreme values occur. Maybe this is just one of them. A more intriguing explanation involves the Eridanus supervoid, a vast underdense region of space, roughly 1 billion light-years across, that lies roughly 3 billion light-years away in that part of the sky. When CMB photons pass through a large void, they can lose a tiny amount of energy, a phenomenon called the integrated Sachs-Wolf effect, which would make that patch of sky appear slightly colder. The math roughly works, but not perfectly. The supervoid alone may not be large or empty enough to fully account for the cold spot. The most exotic explanation, and the one that generates the most excitement in certain corners of cosmology, is that the cold spot might be evidence of a collision between our universe and another universe. A bubble collision in the framework of eternal inflation and the multiverse. In certain inflationary models of the Big Bang, our universe is just one of a potentially infinite number of bubble universes, each nucleating from a background inflationary field, each potentially having different physical constants, different laws, different histories. If two such bubbles collided during our universe's early history, it might have left a distinctive imprint in the CMB, a cold spot, or a ring of altered temperature. Now, this is speculative. This is at the frontier of theoretical physics, not established science. The multiverse remains a hypothesis, a mathematically motivated possibility, not a confirmed reality, and the cold spot has not been definitively identified as evidence for it. Most cosmologists remain cautious, but the fact that we can even ask the question, that a patch of slightly colder sky opens a window onto the possibility of other universes, is itself a testament to how far our understanding has come, and how much further it might yet go. What the large-scale temperature structure of the universe ultimately reveals, from the scorching intracluster gas of the Bullet cluster, to the frigid depths of the cosmic voids, to the ancient ripples of the CMB, is that temperature is not a passive property of matter. It is an active participant in the story of cosmic evolution. Temperature drove the synthesis of the first elements. Temperature determined when the universe became transparent. Temperature controls where stars form and where they don't. Temperature shapes the distribution of matter across cosmic scales. Temperature encodes the history of the universe in the light of its oldest photons. And temperature will write the final chapter too, in the long, slow cooling that leads, over timescales beyond imagination, toward the quiet end we discussed. The universe has a thermal history, a temperature arc that runs from unimaginable heat to near absolute zero, from the first fraction of the first second to the last flicker of the last black hole. And we, these brief, warm, curious creatures on a small rocky world in an ordinary galaxy, exist at a particular moment on that arc, a moment when the universe is neither too hot nor too cold for complexity, for chemistry, for life, for wonder. We are the universe at the precise temperature of consciousness. Isn't that something? But there's one more thing I want to show you before we start bringing this whole story together. Something that connects the very cold to the very distant. Something that ties together everything we've discussed. The CMB, the voids, dark matter, the quantum states of extreme cold into a single, breathtaking vision of the cosmos. It involves the most sensitive thermometer ever pointed at the sky, and what it found when it looked, not just at the CMB, but at the spaces between the CMB photons, at the structure of the universe, at a scale between individual galaxies and the cosmic background itself, changed our picture of how the universe is put together in ways that researchers are still working to fully understand. There is a technique in cosmology so elegant, so cleverly conceived, that when you first understand how it works, you almost can't believe it's real. It doesn't involve building a bigger mirror. It doesn't require a more powerful rocket or a more sensitive camera. It uses something that already exists, something that has been traveling across the universe for 13.8 billion years, and turns it into a thermometer capable of measuring the temperature of gas in galaxy clusters billions of light years away. It's called the Sunyaev-Zeldovich effect, and the story of how it was predicted, ignored, rediscovered, and eventually confirmed as one of the most powerful tools in modern cosmology is one of the great underdog stories in the history of science. In 1972, two Soviet astrophysicists, Rashid Sunyaev and Yakov Zeldovich, published a theoretical paper describing something subtle but profound. When photons from the cosmic microwave background pass through a galaxy cluster, specifically through the hot gas of the intra-cluster medium we discussed a while ago, something happens to them. The hot electrons in that plasma, moving at high speeds because of their high temperature, can collide with the CMB photons passing through, and when they do, they transfer a tiny amount of energy to those photons, boosting them to slightly higher frequencies. The photons gain energy, they get a little push. This means that on the side of the CMB photon spectrum, the galaxy cluster appears slightly cold. There are fewer low-frequency photons than you'd expect, because they've been bumped up to higher frequencies. And on the other side, it appears slightly warm. There's a slight excess of high-frequency photons. The net effect on the total energy is small, but it is measurable. And here's what makes it extraordinary. The magnitude of this effect depends directly on the temperature and density of the gas in the cluster. By measuring exactly how much the CMB photons have been boosted as they passed through a cluster, you can calculate the temperature of the gas those photons traveled through, a thermometer made of ancient light, measuring the heat of structures billions of light years away. When Sunyaev and Zeldovich first published this idea, the technology to measure it didn't exist. The effect is tiny, temperature changes of fractions of a millikelvin in the CMB signal. For years, the prediction sat in the literature, largely unverified, waiting for instruments sensitive enough to find it. Then, through the 1980s and 90s, as radio telescope technology improved, detections began to accumulate. Tentative at first, contested, but gradually, irrefutably confirmed. The Sunyaev-Zeldovich effect is now not just confirmed, it is a cornerstone of modern cosmological surveys. The South Pole Telescope, operating at the Amundsen-Scott South Pole Station in Antarctica, one of the driest and most radio-transparent sites on Earth, has detected thousands of galaxy clusters using this effect. So has the Atacama Cosmology Telescope, perched at an altitude of over 5,100 meters in the Atacama Desert in Chile. Why Antarctica and the Atacama? Because water vapor in the atmosphere absorbs microwave radiation. To see the faint signals of the CMB and the Sunyaev-Zeldovich effect, you need to look from places where the air is as dry as possible. The South Pole, despite being on a continent covered in ice, has remarkably dry air because the extreme cold freezes virtually all water vapor out of the atmosphere. The Atacama, the driest non-polar desert on Earth, offers similar advantages at high altitude. So our most powerful thermometers for the distant universe are built in some of the coldest and most extreme environments on our own planet. Cold helping us measure cold. There's a poetry to that. The galaxy clusters detected through the Sunyaev-Zel'dovich effect aren't just scientifically interesting in themselves. They're cosmological probes, tools for measuring the large-scale structure and history of the universe. Here's why. The number of galaxy clusters that exist at any given cosmic epoch, at any given distance, and therefore any given time in the universe's past, depends sensitively on the underlying cosmological parameters, on the total amount of matter in the universe, on the ratio of dark matter to ordinary matter, on the value of dark energy, on the rate at which the universe is expanding. By counting how many clusters exist at different distances, at different points in the universe's history, and comparing those counts to theoretical predictions, cosmologists can constrain these fundamental parameters with remarkable precision. Galaxy clusters, those most massive of gravitationally bound structures, become rulers for measuring the universe itself, and the temperature of the gas inside them, measured using the Sunyaev-Zel'dovich effect, is central to making those measurements work. Because to count clusters properly, you need to know their masses, and to estimate their masses from observations, you need to understand the relationship between the temperature of their gas and the depth of their gravitational wells. Temperature, again, as a key that unlocks deeper understanding. Now let's talk about what's coming next. Because the current generation of microwave telescopes, remarkable as they are about to be superseded by instruments of genuinely transformative power, the Simons Observatory, currently under construction in the Atacama Desert at an altitude of around 5,190 meters, making it one of the highest astronomical observatories in the world. The Simons Observatory is a new suite of microwave telescopes designed to map the CMB with sensitivity and resolution dramatically beyond anything previously achieved. It will consist of one large aperture telescope with a 6-meter primary mirror and several smaller half-meter aperture telescopes, each optimized for different aspects of the CMB signal. What will it look for? Several things simultaneously. Improved measurements of the CMB temperature fluctuations, pushing our constraints on cosmological parameters to new levels of precision. Measurements of CMB polarization, the way the ancient light is oriented, which carries information about the very early universe that temperature measurements alone can't access. Searches for the signature of primordial gravitational waves, ripples in the fabric of space-time generated during the inflationary epoch, just fractions of a second after the Big Bang, which would appear as a specific pattern in the CMB polarization called B modes. Finding primordial B modes would be, without exaggeration, one of the greatest discoveries in the history of science. It would provide direct observational evidence of inflation, the rapid exponential expansion of the universe in its first fractions of a second, and potentially distinguish between different models of what drove that inflation. The Simons Observatory is expected to achieve first light in the mid-2020s, with full operations ramping up through the latter part of this decade, and beyond it, even more ambitious, CMB-S4, the CMB Stage 4 experiment, a next-generation ground-based facility combining telescopes at both the South Pole and the Atacama with hundreds of thousands of individual detectors, representing roughly an order of magnitude improvement in sensitivity over current instruments. CMB-S4 is designed to essentially extract every last piece of cosmological information available in the CMB that ground-based observations can access. Between these two facilities, cosmologists expect to dramatically sharpen our picture of the universe's thermal history, from the first moments after the Big Bang through the epoch of reionization when the first stars and quasars lit up and reheated the intergalactic gas, through the formation of the cosmic web, all the way to the present distribution of matter and energy. The cold glow of the ancient universe, measured with exquisite precision, will tell us things about the first moments of existence that no other observation can. There's another observatory I want to tell you about, one that approaches the temperature story of the universe from a completely different direction, the Laser Interferometer Space Antenna, LISA. LISA is a planned space-based gravitational wave observatory, a collaboration between ESA and NASA, consisting of 3 spacecraft arranged in an equilateral triangle formation, separated from each other by approximately 2.5 million kilometers, flying in orbit around the Sun. Between the spacecraft, laser beams will be bounced back and forth with extraordinary precision, and when gravitational waves, ripples in space-time, pass through, they will stretch and compress the distances between the spacecraft by amounts smaller than the diameter of an atomic nucleus. LISA is designed to detect gravitational waves at much lower frequencies than LIGO and Virgo, the ground-based detectors that made history in September of 2015 with the first direct detection of gravitational waves from merging black holes. Lower frequency gravitational waves come from different and in many cases larger sources, supermassive black hole mergers at the centers of merging galaxies. The background hum of millions of compact binary star systems throughout the galaxy. And potentially, this is where the temperature connection comes in, a stochastic gravitational wave background from the early universe itself. In the very early universe, phase transitions, moments when the state of the cosmos changed abruptly, somewhat like water freezing into ice, may have generated gravitational waves. These transitions are fundamentally thermal events. They are driven by the cooling of the universe through specific temperature thresholds at which the underlying quantum fields shift from one configuration to another. The electroweak phase transition, when the electromagnetic and weak nuclear forces separated from each other at a temperature of around 100 billion electron volts, corresponding to temperatures of roughly 1 quadrillion degrees Kelvin, occurring around 1/100th of a billionth of a second after the Big Bang, may have generated a gravitational wave signal. If that transition was sufficiently abrupt and turbulent, LISA might detect its echo, raiding the thermal history of the very early universe, written in gravitational waves, using spacecraft flying millions of kilometers apart in orbit around the Sun. LISA is currently planned for launch in the mid-2030s, pending final approvals and funding confirmations. Let's also talk briefly about one of the most ambitious observational programs currently underway, one that uses the cold in a very direct and practical way. The Event Horizon Telescope Collaboration, the network of radio telescopes around the world that produced the first direct image of a black hole's shadow in April of 2019, revealing the supermassive black hole at the center of the galaxy Messier 87, and later the black hole at the center of our own Milky Way, Sagittarius A. In May of 2022, operates at millimeter wavelengths, right at the boundary between radio waves and infrared. The detectors used in these telescopes need to be cooled to near absolute zero to achieve the sensitivity required. The receivers in millimeter wave radio telescopes are typically cooled to around 4 Kelvin using liquid helium cryostats to reduce the thermal noise in the electronics to levels where the faint signals from across the universe can be extracted. So the first images of black holes, objects of literally incomprehensible mass and gravity, warping space-time around them so severely that not even light can escape, were made possible in part by cooling detectors to 4 Kelvin, bringing them to within 4 degrees of the temperature of deep space itself, making the instruments as cold as the universe they were trying to observe. And those images, those rings of glowing gas around an invisible darkness, they represent the boundary of a region where our known physics stops working, where the equations of general relativity, extrapolated to their extreme limit, produce something that cannot exist according to quantum mechanics, a singularity, a point of infinite density. The resolution of that contradiction, what actually happens at the center of a black hole, is one of the deepest unsolved problems in all of theoretical physics. We don't know, and that is one of the most exciting sentences in science. There is a thread that runs through everything we've discussed in this part of the video, through the Sunyaev-Zeldovich effect and the Simons Observatory and LISA and the Event Horizon Telescope. A common theme that might not be immediately obvious but becomes clear when you step back. Every one of these instruments, every one of these observations, is a way of reading the universe's thermal history, of extracting information about temperature, past and present, near and unimaginably far, of understanding how the cosmos moved from the unimaginable heat of its beginning toward the cold and complexity of today. And that history isn't just an academic exercise. It is the story of how everything came to be, how hydrogen became stars, how stars became heavy elements, how heavy elements became planets, how planets, under the right conditions, became warm enough for liquid water and complex chemistry, how the universe cooled just enough, over just the right timescale, for life to have a chance. We are not accidents of the cosmos. We are its outcome, the product of 13.8 billion years of precisely calibrated cooling, of the universe finding its way from fire to warmth to the narrow, precious temperature band where biology becomes possible. And the instruments we build, the telescopes and interferometers and cryogenic detectors, are the means by which the universe examines its own thermal autobiography. We are the universe reading its own story back to itself. Pause on that for just a moment, let it land. Let's come home for a moment, not to a building, not to a city or a country, but to the idea of home, to what it actually means to have one. Because after everything we've explored together, the quantum cold of Bose-Einstein condensates, the ancient light of the cosmic microwave background, the vast freezing silence of the cosmic voids, the thermal autobiography of a 13.8 billion-year-old universe. I think it's worth stopping and asking a question that doesn't get asked enough in science videos. What does all of this mean for us? Not for physics, not for cosmology, for us, for the people watching this right now, on a warm afternoon or a cool evening, in a room with air at roughly 20 degrees Celsius, on a planet that sits at an average surface temperature of around 15 degrees Celsius, orbiting a star that burns at 15 million degrees in its core, a star that, by the relentless mathematics of stellar evolution, will one day expand and cool and die. What does it mean to know all of this? I think it means more than most people allow themselves to feel. Start with where you are right now. You are sitting or lying down or standing on a train or doing whatever you're doing on the surface of a rocky world that formed 4.5 billion years ago from a swirling disk of gas and dust. That disk itself was the remnant of a molecular cloud that collapsed under gravity, a cloud that had been seeded with heavy elements by the deaths of previous generations of stars. The temperature on the surface of the young Earth in its earliest epoch was dramatically different from today. The planet was largely molten, bombarded by asteroids and planetesimals in what we call the late heavy bombardment, its surface a churning ocean of magma. The atmosphere was toxic. There was no oxygen, no liquid water on the surface, no possibility, as far as we can tell, of anything resembling life. Then something changed. Actually, Many things changed over an almost incomprehensibly long time. The surface cooled, a thin crust solidified, water, delivered partly by comets and asteroids, partly outgassed from the interior through volcanic activity, accumulated on the surface. The oceans formed. And somewhere in those early oceans, in conditions we still don't fully understand and actively debate, the first self-replicating chemical systems emerged. Life, not complex life, not animals or plants or anything you'd recognize. Just the faintest, most tenuous beginning of the process that would, over 4 billion years of evolution and extinction and adaptation and innovation, eventually produce every living thing on this planet, every bacterium and fungus and fern and fish and bird and primate, every human being who has ever drawn breath. That process, that entire 4 billion year saga, was made possible by temperature, by the fact that Earth sat at just the right distance from just the right kind of star to maintain liquid water on its surface for long enough for complexity to emerge. Too close to the sun, and the oceans would have boiled away. Too far, and they would have frozen solid. The window, the so-called habitable zone, is real, and Earth sits comfortably within it. But the habitable zone isn't just about distance from a star. It's about the planet's atmosphere, its geological activity, its magnetic field, its axial tilt, its large stabilizing moon. It's about dozens of factors interacting in ways we are still mapping. And the more we study it, the more we appreciate how many things had to go approximately right for this world to exist in its current, life-bearing state. Not perfectly right, approximately right. Life is not fragile in the sense that it requires perfect conditions. The extremophiles we mentioned earlier have demolished that notion completely. Complex, multicellular, technologically sophisticated life, that does seem to require a fairly specific set of conditions. Conditions that may be rare in the universe, even if simple microbial life turns out to be common. Here is a number that I want you to sit with: 8 minutes. That's how long it takes light to travel from the sun to Earth. 8 minutes. The sunlight warming your skin right now, if you happen to be in sunlight, left the sun's surface approximately 8 minutes ago, and before that, the energy it carries, spent somewhere between 10,000 and 100,000 years, slowly diffusing outward from the sun's core, where it was generated by nuclear fusion through the dense solar interior, bouncing from particle to particle in a drunkard's walk toward the surface. The warmth you feel is ancient. The photons landing on your skin were born in fusion reactions that happened long before they ever reached you. Nuclear fire, converted to light, carried across 150 million kilometers of space, arriving at your skin at the speed of light after an 8-minute journey, and you feel it as warmth, as comfort, as the ordinary, unremarkable sensation of a sunny day. There is nothing ordinary about it. The sun converts roughly 600 million tons of hydrogen into helium every single second. Every second. The energy released by that fusion is what drives the weather systems, the ocean currents, the photosynthesis that underpins almost all life on Earth. Every calorie of food you have ever eaten traces back through the food chain to that nuclear fire 93 million miles, 150 million kilometers away. You are running on starlight. You always have been. And here's the thing about starlight that tends to get lost in the physics. It's temporary. The sun is a middle-aged star. It formed about 4.6 billion years ago and has roughly another 5 billion years of hydrogen-burning life ahead of it. In cosmic terms, that's a substantial stretch, but it's not forever. In about 5 billion years, the hydrogen in the sun's core will be largely exhausted. The core will contract and heat up. The outer layers will expand enormously, catastrophically, as the sun transitions into a red giant phase. Its radius will grow to perhaps 100 to 200 times its current size. The inner planets, Mercury, Venus, and quite possibly Earth, will be engulfed or severely affected. Long before that, perhaps in about 1 billion years, the sun's gradually increasing luminosity will have made Earth's surface too warm for liquid water. The oceans will begin to evaporate. The water vapor will rise into the upper atmosphere, where ultraviolet radiation will break it apart. Earth will slowly transition toward conditions more like Venus today, a world with a crushing, scorching atmosphere and surface temperatures hot enough to melt lead. 1 billion years sounds like forever, and from any human perspective, it effectively is. No one reading or watching this today will be alive in 1 billion years. No civilization we can meaningfully imagine will survive that long without transforming beyond recognition. But the point isn't to cause anxiety. The point is to appreciate what we have. We live on a warm world, a world bathed in the light of a stable middle-aged star, a world with liquid water and a breathable atmosphere and a biosphere of staggering complexity and beauty, a world that is, by every measure we currently possess, extraordinarily lucky to exist in its current state. And we know this. We are the first species in the history of this planet, possibly the first in the history of this corner of the galaxy, with the scientific knowledge to understand just how extraordinary our situation is. That knowledge carries weight. It carries responsibility, because understanding the cold of space, really understanding it, not just as a curiosity or a physics factoid, but as a felt reality, changes something in how you see this world. When you know that the average temperature of the universe is 2.7 Kelvin, when you know that the vast majority of the cosmos is dark and cold and empty in ways that beg a description, when you know that the warm, complex, chemistry-rich environment of Earth's surface is not the default state of matter in the universe, but an extraordinary exception, a narrow, temporary, cosmically precious deviation from the cold norm, it becomes much harder to take for granted the warmth of sunlight on your face, the temperature of a cup of tea, the fact that water falls from the sky as liquid rain and not as nitrogen ice, the fact that the air is breathable, that the ground is solid, that other living beings share this improbable warm world with you. All of it, every single bit of it, exists against the backdrop of a universe that is overwhelmingly cold, dark, empty, and indifferent to the particular conditions that make your existence possible. And yet here we are, warm and alive and curious and wondering. Carl Sagan, the astronomer and science communicator, whose work has inspired generations of scientists and curious minds, wrote something in his book Pale Blue Dot that I think about often in the context of what we've been discussing today. He was writing about the famous photograph of Earth taken by Voyager 1 in 1990 from a distance of about 6 billion kilometers as it was leaving the solar system. In that image, Earth appears as a tiny, almost invisible speck, a pale blue dot, barely distinguishable from the scattered light artifacts in the image, suspended in the vast darkness of space. Sagan wrote, and I'm paraphrasing here rather than quoting directly, that our planet is a lonely speck in the great enveloping cosmic dark, that in our obscurity and vastness there is no hint that help will come from elsewhere to save us from ourselves, that Earth is the only world known so far to harbor life, that there is nowhere else, at least in the near future, to which our species could migrate. He meant it as a call to humility, a reminder of how thin the margin is, how precarious our situation, how important it is that we treat each other and this world with care. And when you add to his words the full picture we've built in this video, the cosmic cold, the narrowness of the temperature window for life, the temporary nature of our star's warmth, the almost unfathomable scale of the frozen void that surrounds us, his point becomes even more resonant, not depressing, not paralyzing, but clarifying. There is a concept in philosophy and psychology called the overview effect. It's a term coined by the writer Frank White in his 1987 book of the same name, and it describes a cognitive shift reported by astronauts who have seen Earth from space. A transformation in perspective that comes from seeing this planet, whole, floating, fragile, heartbreakingly beautiful. Against the blackness of space, astronauts describe it in remarkably consistent terms. A sudden, overwhelming sense of the planet's vulnerability, a dissolution of the boundaries between nations and peoples, a feeling of profound connection, not just to other human beings, but to all life on Earth, and a visceral understanding that this thin blue line of atmosphere, this narrow habitable shell clinging to a rocky sphere, is all there is between life and the void. You haven't been to space. I haven't been to space. But perhaps, if we've done our job well today, something of that perspective has come through in what we've been exploring together. Not from a window of a spacecraft, but from the window of physics, from the data returned by Voyager and Webb and Planck and Chandra and the Event Horizon Telescope, from the equations of thermodynamics and quantum mechanics and general relativity that describe the universe with extraordinary accuracy. The overview effect, it turns out, doesn't require a rocket. It requires understanding, and understanding is something available to all of us. Here's what I believe the cold of space is really telling us, not as a physics lesson, as a message. The universe is almost entirely cold, dark, empty, and silent. Life, as far as we currently know, is extraordinarily rare. Warm, complex, conscious life may be rarer still. The conditions that allow beings like us to exist, to look up at the night sky and wonder, to build telescopes and send probes to the edges of the solar system and map the temperature of the Big Bang's afterglow, those conditions are not guaranteed. They are not permanent. They are a brief window in the universe's long cooling history, and we are alive in that window. Right now, at this moment, that is the most remarkable thing I know, not the temperature of the Boomerang Nebula, not the quantum states of neutron star interiors, not even the first image of a black hole. The most remarkable thing is that the universe arranged itself through 13.8 billion years of cooling and expanding and coalescing and exploding and rebuilding, in such a way that here, on this warm, rocky world, something emerged that could understand all of it. You are made of atoms forged in stellar cores. You are powered by ancient sunlight. You carry in your body the legacy of 4 billion years of unbroken biological continuity, stretching back to the first self-replicating molecules in some warm early ocean, and you have, in the span of a few centuries of systematic science, figured out the age of the universe, the temperature of its birth, the structure of its largest features, and the quantum behavior of its coldest corners. That is not a small achievement. That is perhaps the most extraordinary thing that has ever happened in the known universe, and it happened here, on the pale blue dot, in the window of warmth. So the next time you step outside on a cold night and look up, really look up, at the stars scattered across the dark, try to hold two thoughts simultaneously. The first, out there between those points of light, the universe is almost unimaginably cold. 2.7 Kelvin, the frozen silence of the CMB, the empty cosmic voids, the slow, patient cooling toward a final darkness that will unfold over timescales beyond comprehension. The second, you are here, warm and alive and looking. The universe, through you, is seeing itself, wondering about itself, feeling something about itself. And that wondering, that curiosity, that feeling of awe when the scale of the cosmos lands on you like a wave is not a distraction from the universe's story. It is the universe's story, the most recent and most beautiful chapter of it. We've come an enormous distance together in this video. From the basic physics of what cold actually is, to the Boomerang Nebula, to quantum states of matter at the edge of absolute zero, to the thermal history of the cosmos, to what it means for living beings to exist in a universe this cold and this vast. And there is one final chapter left, because there's a question we haven't fully answered yet. A question that's been hovering underneath everything we've discussed, waiting for the right moment. Are we alone in this cold? Is Earth the only warm world with life in a universe of frozen silence? Or are there others out there, other warm pockets, other windows of complexity, where something looks up at the stars and wonders? Are we alone? 3 words, the oldest question humanity has ever asked about the cosmos. A question that predates telescopes and mathematics and the scientific method itself. A question that has been whispered by every civilization that ever looked up at the night sky and felt the immensity of what lay beyond. And today, right now, in the era we're living in, we are closer to answering it than at any previous moment in human history. Not because we've found life elsewhere, we haven't, not yet, but because for the first time, we actually have the tools, the data, and the theoretical frameworks to ask the question scientifically rather than philosophically, to move it from the realm of speculation into the realm of measurement. And the answers, when it comes, if it comes, will be shaped in no small part by temperature, by cold, by the same physics we've been exploring throughout this entire journey. Let's start with what we know about this distribution of warmth in the universe, because warmth, the kind that sustains liquid water, which is our best current proxy for habitable conditions, is not randomly scattered through the cosmos. It follows rules. It clusters around certain types of stars. It depends on atmospheric chemistry, on geological activity, on magnetic fields, on orbital mechanics. We have now confirmed the existence of over 5,500 exoplanets, planets orbiting stars other than our Sun. As of the time this video was made, the count stands there, though it grows regularly as missions like NASA's TESS, the Transiting Exoplanet Survey satellite, launched in April of 2018, continue to find new worlds. The Kepler Space Telescope, which operated from 2009 until it ran out of fuel in 2018, found over 2,700 confirmed planets on its own, transforming our understanding of how common planets are. And what Kepler and TESS and other surveys have told us is extraordinary. Planets are not rare. Planets are ubiquitous. The early assumption, barely a generation ago, that planetary systems might be unusual or exotic has been thoroughly demolished. Virtually every star we look at carefully enough appears to have planets. Many have multiple planets. Some have planets in their habitable zones, the regions where temperatures might allow liquid water on a rocky surface. The nearest potentially habitable world we know of is Proxima Centauri b, a planet orbiting Proxima Centauri, our nearest stellar neighbor at 4.24 light-years away. Discovered in 2016 through radial velocity measurements, Proxima b orbits within the habitable zone of its host star, but Proxima Centauri is a red dwarf, a small, cool, dim star, and red dwarfs present their own set of challenges for habitability. They are prone to violent stellar flares, blasting their nearby planets with ultraviolet and X-ray radiation. Their habitable zones are so close to the star that planets there are likely tidally locked, one side always facing the star in permanent day, the other in permanent frozen night. Whether tidally locked planets can maintain habitable conditions is genuinely debated. Some climate models suggest that atmospheric circulation could distribute heat from the day side to the night side effectively enough to maintain liquid water somewhere on the surface. Others suggest the conditions would be far too extreme. We don't know yet. It's an open question. The TRAPPIST-1 system, discovered through observations by the TRAPPIST telescope in Chile and subsequently studied in extraordinary detail by Spitzer, Hubble, and now James Webb, contains 7 Earth-sized planets orbiting a small red dwarf star about 40 light-years away. 3 of those planets sit in the habitable zone, 3 potentially warm worlds, in a system close enough that we can actually begin to study their atmospheres with the James Webb Space Telescope. Webb has already begun that work. early observations of TRAPPIST-1 planets have looked for atmospheric signatures, the chemical fingerprints that would indicate the presence of a substantial atmosphere, and potentially the molecular signatures associated with biological processes. The results so far are tantalizing but not conclusive. Some planets appear to have little to no thick atmosphere. Others remain to be fully characterized. The work is ongoing, painstaking, and one of the most exciting scientific programs currently underway anywhere in the world. Let's talk about what we'd actually be looking for. Biosignatures. A biosignature is any observable property, a chemical compound, an atmospheric ratio, a surface feature whose presence strongly suggests a biological origin. The most discussed biosignature in exoplanet science is oxygen. On Earth, free molecular oxygen makes up roughly 21% of the atmosphere, and almost all of it is maintained by photosynthesis. Without continuous biological production, oxygen would quickly be removed from the atmosphere through chemical reactions with surface rocks. Its presence in abundance, combined with methane, which reacts rapidly with oxygen and therefore shouldn't coexist with it unless something is continuously replenishing both, would be a powerful indicator of biological activity. Other candidate biosignatures include nitrous oxide, phosphine in certain contexts, specific ratios of carbon isotopes, and what's called a vegetation red edge, a sharp change in reflectivity at specific wavelengths that results from the chlorophyll in plant leaves and has no known abiotic explanation. None of these are definitive on their own. Each could, in principle, have non-biological explanations in specific circumstances. The challenge of biosignature detection is not just sensitivity, it's interpretation. How do you confidently distinguish a biological signal from a geological or chemical one? This is one of the central challenges of astrobiology, and solving it requires understanding planetary atmospheres, stellar radiation environments, geological processes, and the chemistry of life itself, all simultaneously. James Webb is beginning to make real progress on the atmospheric characterization side. But for genuine biosignature detection on Earth-sized planets in habitable zones, the next major leap will likely require a new generation of space-based direct imaging telescopes. Concepts like the Habitable Worlds Observatory, currently in the early planning stages at NASA, which would be designed specifically to directly image Earth-like planets around Sun-like stars and take spectra of their atmospheres. These missions are ambitious, they are expensive, they will take decades to realize, but they represent the clearest path toward one of the most significant possible discoveries in the history of science. And what about the possibility of life not based on liquid water at all? We've mentioned Titan before, that eerily Earth-like moon of Saturn with its liquid methane lakes and orange hydrocarbon skies and surface temperature of roughly -179 degrees Celsius. The question of whether life could exist in liquid methane rather than liquid water is one of the most genuinely open questions in astrobiology. Water is an extraordinary solvent. It has properties, its polarity, its hydrogen bonding, its ability to dissolve an enormous range of organic compounds that make it exceptionally well suited for the kind of chemistry that life requires, as we understand it. Liquid methane is far less polar, far less reactive, far more limited in the chemistry it supports at low temperatures. But here's the thing. We developed our understanding of the chemistry of life by studying the only life we know, life on Earth, based on water. We cannot be certain that our framework applies universally. We cannot rule out the possibility that in the cold methane lakes of Titan, or in the subsurface oceans of icy moons like Europa and Enceladus, or in environments we haven't yet imagined, chemistry of sufficient complexity for something we might recognize as life could emerge. Europa, Jupiter's ice-covered moon, slightly smaller than Earth's moon, is one of the most exciting astrobiological targets in the solar system. Beneath its icy surface, which is carved with cracks and ridges from the gravitational flexing of Jupiter's enormous tidal forces, a global liquid water ocean is believed to exist in contact with a rocky seafloor. The conditions may not be entirely unlike the hydrothermal vent environments on Earth's ocean floor, where communities of organisms thrive in complete darkness, powered not by sunlight but by chemical energy from the rocks. NASA's Europa Clipper mission, launched in October of 2024, is currently en route to the Jovian system. It will conduct dozens of close flybys of Europa, mapping its surface, measuring the thickness of the ice shell, characterizing the composition of material ejected from the Moon's surface, and looking for signs of current geological and perhaps chemical activity that might hint at habitability. It is expected to arrive at Jupiter in 2030. Enceladus, Saturn's small, icy moon, has already revealed something extraordinary. The Cassini spacecraft, before its mission ended in 2017, flew directly through plumes of material being actively ejected from cracks near the Moon's south pole. The material in those plumes included water vapor, ice particles, carbon dioxide, methane, molecular hydrogen, and complex organic molecules, including some with masses suggesting relatively large carbon-rich compounds. The presence of molecular hydrogen in particular suggested active hydrothermal chemistry on the seafloor of Enceladus's subsurface ocean, a world smaller than the state of Texas, covered in ice, in the outer solar system, where temperatures at the surface reach around -200 degrees Celsius. And yet beneath that frozen crust, warm water and active chemistry, the cold surface hides a warm heart. Let's zoom out one final time, because the question of life in the universe isn't just about individual planets and moons. It connects to one of the deepest puzzles in all of science, the Fermi paradox. Named for the physicist Enrico Fermi, who reportedly asked the question at a lunch conversation in 1950 at Los Alamos National Laboratory. The paradox is this: given the vast age of the universe, the enormous number of stars, the apparent ubiquity of planets, and the relatively rapid emergence of life and intelligence on Earth, where is everybody? If intelligent life arises reasonably often in the cosmos, and if even a small fraction of intelligent civilizations develop the ability and desire to explore or communicate across interstellar distances, the universe should by now be filled with evidence of their presence. Signals, artifacts, something, and yet we have found nothing. Silence. The great cosmic quiet. Many explanations have been proposed. Perhaps the emergence of complex life requires an extremely rare combination of conditions, rarer than we currently appreciate. Perhaps intelligent civilizations typically destroy themselves before reaching the technological level required for interstellar communication. Perhaps the distances involved are simply too vast and the timescales too long for any meaningful contact to occur even between civilizations that do exist. Perhaps our search strategies are wrong. We've been listening for radio signals since the first SETI observations in 1960, but a truly advanced civilization might communicate in ways we haven't yet conceived. Or perhaps the most humbling possibility: we are alone, or nearly so. Perhaps the emergence of consciousness in the universe is so rare that, across a cosmos of hundreds of billions of galaxies, each containing hundreds of billions of stars, the occasions when it happens are so widely separated in space and time that they never intersect. We genuinely don't know. The Fermi paradox remains unresolved, and every year of continued cosmic silence both deepens the mystery and sharpens our tools for addressing it. What we can say is this: the cold universe we've explored today, vast, dark, ancient, overwhelmingly empty of warmth, is also vast enough that the probability of Earth being the only warm, complex, life-bearing world in it seems difficult to accept on purely statistical grounds. The numbers are almost too large to permit such a conclusion, but statistics and physical reality don't always align, and until we find the evidence, the question stays beautifully, agonizingly open. Here's something I want to leave you with. In the summer of 2012, the Voyager 1 spacecraft, that same remarkable machine we talked about in Part 4, now over 23 billion kilometers from Earth, crossed a boundary, a real physical boundary, the heliopause, the edge of the heliosphere, the bubble of solar wind and magnetic influence that our sun projects outward into space. Beyond that boundary, the solar wind ends, the sun's direct physical influence stops, and the environment of interstellar space begins. For the first time in human history, something we made was no longer inside the solar system. It was out there, in the interstellar medium, in the cold between the stars. The temperature of the plasma outside the heliosphere, measured by Voyager 1's instruments, is around 40,000 to 50,000 Kelvin. That might sound hot, but it represents a plasma so thin, so few particles per cubic meter, that the total thermal energy is minuscule, the density is almost nothing. The cold in the way we've been discussing, the cold of the CMB, the cold of the vast distances, still dominates. Voyager 1 is out there, in the true interstellar medium, and around it the universe hums at 2.7 Kelvin, and it carries with it, among its instruments and its gold-plated phonograph record of sounds and images from Earth, something invisible but real, the fact that we tried, the fact that in 1977, human beings, creatures who had existed on this planet for a few 100,000 years, who had only just figured out how to leave the surface of their world, decided to build a machine and throw it at the stars. Not because it was practical, not because it would bring any immediate return, but because curiosity demanded it, because the universe was out there, cold and vast and magnificent, and we wanted to know what it was like. That impulse, that irreducible human hunger to understand, to explore, to reach beyond what's comfortable and known, is, I believe, one of the most profound things about our species, and it is the direct descendant of the same impulse that led early humans to look up at the night sky and ask what those points of light were. The tools have changed, the scale has changed, the questions have deepened and multiplied, but the impulse is the same. So here is the brutal truth about how cold space actually is. Space is cold beyond anything your body can experience and survive. It is cold in ways that require quantum mechanics to fully describe. It is cold with the ancient, patient cold of a universe that has been cooling since the moment of its birth and will continue cooling for trillions of years beyond anything we can meaningfully imagine. The average temperature of the cosmos is 2.7 Kelvin. The coldest natural place we've found, the Boomerang Nebula, sits at approximately 1 Kelvin, colder than the universe itself. The quantum states that emerge near absolute zero, superconductors, superfluids, Bose-Einstein condensates, may exist inside neutron stars and at the hearts of some of the most extreme objects in the universe. The CMB, the faint thermal afterglow of the Big Bang, fills every corner of the observable universe and carries within its tiny temperature fluctuations the entire story of cosmic structure formation. Dark matter shapes the cold architecture of the cosmic web. The universe is heading, over unimaginable timescales, toward a final state of near-absolute cold that physicists call the heat death. And in the middle of all of this vast, dark, freezing cosmos stretching 100 billion light-years in every direction we can observe, there is a small, warm, rocky world, orbiting an ordinary star, wrapped in a thin, fragile atmosphere, covered in liquid water, alive with 4 billion years of biological complexity. And on that world right now, there are beings made of ancient stardust who can look up at the cold dark above them, measure its temperature to fractions of a millikelvin, trace its history back to the first fractions of the first second of existence, and feel, genuinely feel, something profound about what they find there. That is not a small thing. That is, as far as we know, the most extraordinary thing in the universe. The cold of space isn't something to fear, it's a context. The grandest, most humbling, most clarifying context imaginable for the warm, brief, luminous thing that is a human life. Every moment of warmth you experience, every sunrise, every warm meal, every embrace, every afternoon when sunlight comes through a window and falls across a floor, is happening against the backdrop of that cold, is made more precious by it, is defined by it, the way a single candle flame is defined by the surrounding dark. You are here, warm and conscious and wandering, in a cold universe that produced you against extraordinary odds and has no obligation to continue doing so. Look up. Stay curious. Never stop asking what's out there, because the universe, cold and vast and ancient as it is, apparently made beings capable of loving it, and that is the most beautiful truth of all. And if the cold of space just blew your mind, wait until you see what it does to a starship. Click the video on your screen right now to explore how long a starship would actually survive in deep space. Trust me, you don't want to miss this one.